Okay, looks like we're live. Today I want to have a look at tree nodes in Ethereum. So I have been doing a little bit of digging on it already. And there is a tree package in Geth, Go source, GitHub, Geth, Go-Ethereum. Go-Ethereum. Yeah, so there is this tree structure here. And first looks at it, it doesn't seem too complicated. So there is 400 lines, and it really is, you create a new tree structure and there's an update and remove functions on it. So here's a tree. It needs to have a database backend and a root node. I think the purpose of this is to say you give it access to your chain database and you name the key that is that you're going to use for the root, and then you can have it sitting alongside other trees in the same database. So you create a new tree using this new function, pass it a hash, which is going to act as the key for the root node. And then you've got this database, which I assume is just going to be chain data in the Ethereum Geth node. And it really, at this point, only gives you a get, gives you a update, and it gives you a delete, and it also gives you an iterator. Now the issue I've kind of hit at the moment is that Patricia trees, modified Merkle Patricia trees, are kind of complicated in that they use the address of an account as the path down a tree. Tree radix. So you go, give me a picture. So you got a tree, and these are your nodes, and these are going to be the accounts saved in RLP form. And this Romane, R-O-M-A-N-E, get into here, is actually the hex address of the account. So you follow the account's address down, and it'll give you it. And I've been running this and playing with it, and I made a little project, just a test project to go through it. Up into Darcy's tree test main. And over here, I've just imported the Geth packages, the database, the tree, the common. I create this new tree here. And you can update by putting a key in there. You get this hash, gives you the root node, so it can tell you what it is. Don't know what that is. And then you can iterate through it and get what the values are in it. So if I run this, go run main. Input and not use bytes. Error. many arguments got the tree, don't you? Okay, cool. That was because I was practicing. Yeah, and it runs. So the only thing that's happening is down here, it's printing the key and the value. Now I've put here key 1 into it with this value of 99.99.99, and that was just ripped straight out of a test package that was in Ethereum. And you also call Go-Get. So if you go Trie.get byte key 1, I believe, 0 format.print line x. See if that works. Probably won't. What have I got to do? Undefined x. It. Yeah. So that just gets x, which is key 1. So you go search for key 1. And that all seems well and good and simple, but it's exactly the same as a database at this point. Like, there's no difference between it and just writing straight to this. Here I've got a mem database, so it's not actually being saved into anything. But if you've got the level database, they have the exact same function. So I don't see where it's doing anything special at the moment. And that's kind of where I'm wanting to dig in. Because really, if you look at it, you call this new, it creates the database, calls this resolve hash, get calls trie.get, which calls trie.get here. You got a key. So one of the things that they're big on is that in Patricia trees there are 2 types of nodes, which are this is what they all meant to be are, but they can shorten some. So there is a this isn't even talk about it. Yeah, okay, here. A branch and a leaf node, which is where they're saying a value and a short node here. Because these 2 items are essentially the same in the implementation. So this is a long form where it's got 17 items in an array, and this one is a short one where it's only got 2. And the short one is just to navigate the tree a bit better. So if you get a big long list of nothing else but that one, so if this didn't exist, it's all one, and that one didn't exist, it's all one line, you could shorten it, right? They do that here with OM and AN, but in the trees they're sort of simpler, so they try to they keep it to 1 in the original design, but the way they've implemented having multiple items is this extension node, which I believe is this short node or value node. So when we call get, it's got the key, it's got the position, and you give it the root node. It goes through switch n. Where's n? N equals original node dot type. So it looks at the root node you've passed it through. It looks if it's a value node or a short node. If it's a value node, it just returns the node straight away. If it's a short node, it looks the length of the key minus position. It's less than the length of n key. So this looks like it takes the length of your key and looks at the node's key. And if they're not equal, the key is not found in a tree. Okay, here we go. Full node, short node, value node. Sets a short node, full node is what the two we were looking at before. A value node is the actual value, I believe, goes into a full node. So the value here. So it looks like they're actually working with it. And all these special nodes, and they're traversing it. And it's just implemented so you don't have to deal with it. Which is nice. And I mean, going forward, I won't have to worry about it. But I just want to see how they're doing it. And how we can play with it as well. And I think this resolve hash is kind of key to it at the moment, because they keep calling that. Go back into Ethereum. Resolve hash. It's in tree. So that's resolve hash. So takes bytes to hash. Takes this hash node, turns it into its hash. Node.db.node hash does not equal nil, return null node. Okay, so that's actually getting out the node. So you're calling node on the DB. And they've got a special database in this tree as well. They're very like looking, which is really interesting because they just wrap the database. So they got a level database, which they're wrapping in the ETH database, which they're wrapping in this tree database, and they're putting this tree around it. So they wrap it like 4 times. I'm sure it's necessary, but it's a bit of a headache to get your head around. So, what's that DB node do? DB.node. Now let's look at the database too first. So in the database, there's going to be a node function, possibly. Uncache size. verify integrity. DB nodes. Commit. Where are you? What are you doing? Cap. Flush is old. Not interested. No reference to child. Node. Dereference. Removes an existing reference. Reference. So talk about, ooh, there's a node. Nodes. Capital. Nodes retrieves the hashes of all the nodes cached within this memory database. Do I have access to the node in the tree? Can I just call that? What will that do? Extremely expensive, do not use. Iterates through every single one. No, I do not. But I do have access to the database. Maybe I can just do that. So if I make the database here, db.new database, eth database dot new mem database, detail dirt. db equals. Now if we set this to db here, and then we should be able to call that nodes and see if that spits out anything different. See if that works first. Go back into Darcy's. Try test. And go build and see if that just compiles. Undefined eth database, new database. No, it was tree. Try tree. It looks like that compiled. So we go main, go. Go run main even. That should spit out our one key still. Testing tree. So let's bring back that one. Remove that, bring these back. Bytes, bytes. Cool, so we got two keys that I originally was putting in. Key 1, key 2, 9999s, and 32 bytes of 1. So that's all working fine. Now, if I look at node, database, there's this node which retrieves a hash of all nodes. An array of hashes of nodes. Nodes equals db.nodes. Nodes declared and not used. Print. Let's get rid of these again. It's an empty array. So what's new do? Does that take it, point it to a database? This is where I have to figure out if it's maybe. So that didn't work. There's a chance that it's because it's working on a reference or a copy or something. But I don't think so. I thought it'd be working on the original. Who knows? The other issue is they got this secure trees as well. They talk about quite a lot, which I don't fully understand at all. So my next tactic's going to be to actually find where they're playing with it in here. So we'll get out of here for a sec. We'll get out of here. And if I look up Trie.new and find what it's spitting out. So download a tests. Tests aren't going to be any good. API. It's making a new iterator over it. Core blockchain.go. That could be something. Block root state cache try database. Interesting. State dump sync state database. Core state database is a maybe. Yeah, let's have a look at that one. Core. State database. Caching layer top of state tree. For each storage, CB takes a function. Database gets state object address. New iterator get tree. Database node iterator. So they're iterating over each one in the tree, and they're calling this function on it, I guess. CB. Yeah, if value is dirty, SO dirty, get state object, get the dirty object, yeah, so get the most recently played with, call it on the key and the value. Get state object and address. So I think you pass it a node and it'll get this iterator, go through all the accounts below it. Oh, okay, yeah, so it goes through them all and calls that function on them, whatever you're going to do with it. Not what we want though. What else is there? Secure tree called without a database. Tree.new database. Here's all the light implementations. Core state database. So tree.new again. So when you got a new database, tree is an interface that has try get, try update, try delete. So that's literally just wrapping that tree file structure that I had before. The database object is also an interface. It has an open tree and it has a copy of the tree database. ETH database. So where's that implemented, do you reckon? Tree.new database. So it looks like it just wraps the, they got a casing database, which is, it implements that one, which just has a tree new database. With just a DB, and did he call nothing else? I thought they'd given an error. Casing database. Opens main account tree. So it does, that's just wrapping. They've made an interface to this here, which just wraps the tree database. You got to open a tree. New secure root. So they're using the secure, which is the same thing, but they put prefixes on the key, I believe. I haven't dug too much into it. Open storage tree of an account. New secure root database. Do they even use address hash in this call? They don't. Copy in it, contract code. So you got this state database. We looked at the state object. And what did it say? Because this just has the actual object, which is the state object, which that is what's getting saved into the tree. They encode it into RLP and then they save it. And maybe there's a make hash that I kind of ignored. Get state, nah. State object. Back in the state database. Create account creates a state object. So location layer on top of the state tree. So it's got that database. It's here, which is wrapping the other one. Again, you wrap in a level database in like 8 ways. They got a mapping of addresses and a tree. The thing that's a bit scary is that tree looks like it's in the namespace of main test. What's it say here? Testing's always good. Nothing. It does nothing. They haven't built tests yet. Iterate a journal state database sync. Nah, it's got to be in this. I got too many. Of these open. All right, so they've got new state database, which you pass in the root hash to database. They call open tree on it. Error reset. Clears out all ephemeral state objects from the state database, but keeps unlaid state tree. Add a log. Get logs. Self.t hash self is the state database. Journal append add log change. No, not logs. Pre-image. Nope. Add refunds. No. Exist. Given account address exists in the self.getState object. Where is that defined? Where is it? They're got to be somewhere here. State database. Get state object. I'm in the state DB file. Delete. Here it is. Why did I miss that so many times? Because I'm retarded. Retrieves a state object given the address, returns nil if not found. So you pass an account address into the state database and we'll find it. Object, if it's in, so they've got an array of them, a mapping saved already that's not saved in a tree. And they'd like to use that first. If not, they call Trie.go. Which is on the tree itself. So they call this Trie.go. Returns a value for a key stored in a tree. The value must not be modified by the caller. The key is address slice, common address. So we get it to an array of bytes, key bytes to hex. So turn it into a hex value. Value root equals t.trie.get in the lowercase. Root that if not return error. Check it to root and key. Origin node. Say I do this recursively. They look at the root node. If it's a short node, they navigate down to the new node. Then they call it on value key original node. Pause. So they're saving how deep they are in a tree. If it's a value node, they return it. So if you're navigating it and they get to a value node, they actually give it to you. Full node. Value new node. Did resolve and try get children. N.children. So if it's a full node, they've got this children. And the children's going to be where it is got 17 values, 16 of which are the 16 byte, 16 bits options. So it's 0 to F for 2 bytes, or the value itself, which they talk about here. Branch. Yeah, there's like 16, which you can keep following down, or the final one is the value itself. This doesn't give a great example, unfortunately. So we'll show that in code. Node. There are full nodes. It has children, which are also nodes. And a node flag. So it gets the encoded value from that, decodes it, puts it into a state object, and returns a state object. Cool. So that does everything there. It's just delving in a bit more to figure out what is going on. So maybe the issue is I've taken it and I'm just using a tree as a database as is. They're actually going to the effort of building the nodes and stuff. Original node, t.root, key. Maybe I should do that. So if I go back in my test one, cd try. No, I want my one, which I've closed. So if I go up a few directories to mine test main, so what are they calling it? Get state object self dot try get address. They call small root on it, which gives them a node. Searching for root in this file is probably a mistake. Root. Just a root. Commit. Hash root. Empty root. Root is a node. Bugger. So we don't have access to that. But I did put it in there. That was me putting it in there. Common.hash is one. screwed that up so much I couldn't figure it out. Res. Go run main. Does that work? No hex utils because I've hidden them away. Cannot use as type byte. Res. Gotta remove it again. Unexpected hex util at the end of statement. Testing try. So it's given me an array of. What does it give me? Hash. Dot bytes. Array of bytes. T.hashroot. Yeah, so they update the cached hash root. Hash node empty root bytes. Database on leaf callback. New hasher. Return hash to pool. So there's a hasher. Up bit tree. New hasher. Cache limit on leaf callback. Collapses a node into a hash node. Also returning a copy of the original node initialized. Hash n.cache. T.root equals nil. Database. So they changed the T.root here equals cached. So cached root returns root. Hash root. What? H.hash. They pass it to T.root anyway. it's nil, empty root.bytes. Okay, so this is not getting me where I want it to be. Update state object. State object.address. And they call try update. Address and data. So I'm going to actually see if I can make a state object in my test. And if I can make one, write it to the tree in exactly the same way and see what happens. Set up test. Test null. So I'm assuming somewhere in this test suite. I got too many things open. Screwing with my head. They are creating a new state object. So they make an address, which is this state object 1 byte to address state object 1. Storage address data for 0 equals that. What do they do with it? They make this, and then they call state.setState. So you make the state object in exactly the same way as you make a tree. Xstate. New database, new mem database. DB. So make this state object. State suite. But what is the namespace of it really? Common crypto. Package state. So they're making this, and then they're saving it to set up test is not super exciting. Set state. Then they call set state. Object data 0. And then they get it straight away. What's that give us? And then they change it heaps. So they make the state object, set it in state, get it back out. Then set the balance to 42, set the nonce to 43, set the data, the code to cafe. Yeah. Suicide deleted set state object. Let's get rid of all this. GGGT clear command not find. Cannot find it in state. Where is it then? Core. I don't have HashiCorp. Go get github.com/HashiCorp/golang-liu. Non-declaration outside function body. What? Core types block 103. There's an error in their thing. What's going on there? Core. Maybe it's where I've typed something in stupid, screwed it up. Core types block. Undefined new. There's lots of shit going on there and there. No, because I haven't done it. State dot undefined to address. State 27, 24. State.set state. X. Down to 28. X state. $29. Big, they've got. Math big. So many errors. cannot use database as type state database. Tree database? Oh no. What do they use? They got a state wrapper around it, don't they? State.new database. Cannot refer to unexported name to address. Bugger. What? Xstate get state object. So they don't actually make it from scratch there because they use internal methods. Just set state object. Undefined crypto. So that doesn't actually, that's painful. I'm trying to learn how to create a state object and they do it all with internal methods. So that's not how they actually do it. Who knows? Alright, so that didn't work either. Get rid of all this state stuff. Go. Ethereum. Go. Ack state dot new. Where's that come out? In lots of places. Lots and lots of places. So I got a downloader. Download a test. Maybe that'll do it. Alright, up and look at the downloader. Downloader. downloader.go, downloader test. Why they commented out? Nope, that doesn't do it either. So API tracer, get block number, chain makers. Alright, let's try that. Core.chainmakers. So they make a new state. Block receipt equals generation blocks. Nah, they do nothing with there either. Blockchain.go. So in this big function, which I assume is the new. Geez, it's huge. Insert chain. We'll execute the actual chain insertion. So you got the state here, passing the state, the block, and the state. State.cache. Validate state. So this BC processor is taking a block and a state and writing it to it. If we trace that a little bit, maybe that'll help. Just what is the processor? Blockchain processor. Block processor interface. So it has to be under the blockchain name space. So we're going to core block. Blockchain test. Blockchain.processor, state processor. It's a basic processor which transitions. Okay, so that's it there. So in here, there's a state processor. There it is. And this is called by set processor, takes a processor. Yeah, so we make a new state and we call process on it. And what it does is it updates the state according to the Ethereum rules by running the transaction messages. So it takes a block. If the DAO for in block.transactions, prepare hash block hash. Receipt equals apply transaction to the block state database. Alright, so we got another one. Apply transaction. Attempts to apply the transaction. So this has got like 1001 parameters being passed to it. Headers transaction. So type.transaction. So they pass the transaction to it. They get the message. Cool, very good. They create a virtual machine context. And they call apply message GP gas pool message VM environment. So they're making a new EVM, passing a context to database and a config. Apply message to that. Update the state. Here we go. No, okay, so this apply message must make some changes. And then you call finalize on the state database. New receipt. Transaction hash. Transaction gas used, so they make the receipt up. Get the logs. It's quite interesting actually. Cool. So it's this apply message. Which is not here. Core. State transition. Replaces old bytes returned by the EVM. The new state transition. So they create this state transition structure. And then they call transition database on it. Which is this one. EVM, where's the state? What are they calling on the state? So up here there's a state transition. They got the state database. So apply message makes a new new state transition structure, and they call transition database, and it's got a st.state somewhere here. Set nonce blah 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 state.addBalance. Set nonce state transition. Increment the nonce. Get nonce of the sender address and add it for 1, and they set it. Add balance. In the Coinbase. Okay, cool. So this is where they add the transaction fees to the Coinbase, the other one. They call it EVM refund gas if it's an error. So they're not doing much over there. Refund gas, st state.getRefund. Add balance for the gas used. Alright, so let's look at this set nonce. So in the state, core state, there is a set nonce. Set nonce, state database. Do I have that open? Make state object. Oh, no, it just changed on a state object. So where's it get saved? It's in that finalized, you reckon? The finalized method in the state DB. So we got all, they do not exist. State database.delete state object. S.update state object. That's looping, isn't it? For everything in the dirty journals, update the state object. writes the given object to the tree. So they get the address, code it, and they call try update. So we were looking at this before. So it just looks like everything they're wrapping means you don't have to think about the tree. So they play with the state object, they call the virtual machine, they call the update finalize, so finalize, and that iterates through all the changes and calls this update state object. It takes the state object and just writes it into the tree. And I guess that's kind of nice because they don't want to think about digging into the tree and its complexities. They just want to work with it as a database, really, which is nice. And they want the underlying stuff to be faster. Still, I would really like to be able to explore it a bit better. But I mean, I've gone through quite a lot today, and there's quite a lot of interesting stuff. And I would like to play with the Merkle trees with the Go implementation so we can see how they work. But I'll do that later, and I'll probably do some more exploring on my own to figure out how that's going on, because there's a lot of nothingness happening. Anyway, thanks for watching. Take care.